Hello everyone, today we will continue the discussion in journey design. Actually, in the lecture today, we will finish all the rest topics in this area. In the last lecture, we introduced the estimation of two inflow rates, surface infiltration and groundwater seepage. The third one we want to learn is meltwater from ice lenses. Usually, the meltwater is generated when the temperature of the pavement is increased and higher than the freezing temperature. The rate of the meltwater seepage from the consolidating soil is at a maximum immediately following the thawing and decreases rapidly as the time increases. We can see that the maximum seepage rate only lasts for a very short time. So the design inflow for the meltwater rate is taken as the average during the first day after thawing. And the value of Qm is determined by the average rate of heave, the permeability K of the subgrade soil, and consolidation pressure sigma P on the subgrade. The figure here shows the relationship between the inflow rate of the meltwater seepage Qm and the average rate of heave, consolidation pressure, and permeability of the soil. Basically, we can see that when we increase the average rate of the heave, Qm will be higher. In addition, if we increase the consolidation pressure, we can also see the increase of the inflow rate. Similarly, for the permeability, if permeability is higher, Qm is also higher by a fixed value of the rate of the heave and sigma p. The table here shows the typical heave rate for different types of the soils. Basically, the heave rate is determined by the soil types and also the gradation of the soil. We can use this kind of typical values to determine the heave rate and estimate the inflow rate for the meltwater seepage. Now let's go through one example for the calculation of the inflow rate from the meltwater seepage. In this example, we assume that the COT sand in the example from lecture 12 is also applied, and it has 9% of the particle finer than 0.02 mm. Also, it's subjected to frost action. It wants us to define the inflow rate Qm. In this example, we assume that the unit weight of the concrete is 150 PCF and 115 PCF for the drainage layer. The permeability of the sand is 0.34 feet per day. So in the solution, we should first find out the consolidation pressure, sigma p. Also, we need to identify the average rate of the heave. So for the sigma p, it is actually determined by the unit weight of the materials and the thickness of each layer. For the thickness of the PCC, it's 9 inches, and for the thickness of the drainage layer, it's 6 inches. With that, we can get sigma p equal to 150 times 9 over 12 for feet, plus 115 times 6 over 12 for feet. The value is 170 PCF. So that's the consolidation pressure. So we will see a line between 100 PCF and 200 PCF, which would be the line here. It's 170. In addition, we also need to find out the average rate of the heave. So we say that RH is determined based on the percentage of passing, that is 9%. Then we can check the table that we showed previously with COT sent and 9% passing. The heave rate is set as 9 millimeter per day. And we can see that the value we're gonna choose is here. Then based on this frost heave and the line with sigma p equal to 170, we can find out the value of Qm over square root k as 0.74. So we have Qm over square root k is 0.74. That is the value here. With that, we can get a Qm equal to 0.74 times the square root of k. K is the permeability, which is 0.34. So we have Qm as 0.43 feet cube per day per feet square. So that's the way for us to find out the inflow rate from the meltwater seepage. With the estimated inflow rate of surface infiltration, the groundwater seepage, and meltwater, we can then determine the design inflow for the drainage system. Usually, the design inflow is the summation of the inflows from all sources minus the outflows through the subgrade soil. However, the outflow usually is determined by the permeability of the soil on the water table at the boundaries. At most of the time, we assume that the outflow rate can be ignored. In that sense, the design inflow rate can be determined by the following two conditions. If there's no frost action, then the design inflow rate, Qd, could be set as Qi plus Qg. And we know that for most of the situation, the groundwater seepage inflow rate is very small. We can try to ignore that in the design. So we will usually assume that Qg equal to 0, in that sense Qd equal to Qi. If there is a frost action, then we have to consider the impact of the meltwater. In that sense, Qd equal to Qi plus Qm. Now let's take a look at one example for the estimation of designed inflow rate based on the result from the three previous examples where we estimate the inflow rates for the surface infiltration, groundwater seepage, and meltwater. We also want to find out the inflow rate to the longitudinal drain. From the previous example, we can find that the infiltration rate is 0.46 feet cube per day per feet square. For the groundwater seepage, we have Qg equal to 0.057 feet cube per day per feet square. We also find that Q1 caused by the groundwater, which is the longitudinal drain, is 0.22 feet cube per day per feet. And at last, for the meltwater, we have Qm equal to 0.43 feet cube per day per feet square. With all this information, we can then estimate the design inflow. So first, if there's no frost action, we have the design inflow Qd as Qi plus Qg. That is 0.46 plus 0.057, which gives the result as 0.517 feet cube per day per feet square. And then we can find out the longitudinal drain. QL, it actually equals to QD times L plus Q1. Here, L is the total width of the pavement including the shoulder. So we have 10 plus 24 plus 10. Here 10 is the width of the shoulder, 24 is the width of the pavement, that is 44 feet. So we get the result as 0.517 times 44 plus 0.22. So the result is 23.0 feet cube per day per feet. And if we have the first action, then QD will equal to QI plus QM. So that is 0.46 plus 0.43, that is 0.9089. And we can find out the inflow to the longitudinal drain as QD times L. As here we don't have any groundwater seepage, so we don't apply Q1. With that we get 0.89 times 44, that is 39.4.2 feet cube per day per feet. So that's the way for us to find out the design inflow and the inflow to the longitudinal drain. Besides the inflow rate to the drainage system, the other thing we need to think about is the drainage capacity. Usually the capacity of one drainage system is the capacity of both drainage layer and the collector pipes. For the design of the drainage system, we want to make sure that the capacity, which is the maximum outflow rate, is higher than the inflow rate to the drainage system. First, for the drainage layer, usually there are two requirements for the drainage layer. At first, the layer should have a steady state capacity which is larger than the inflow rate, so that it won't retain any water in the pavement structure. Second, it should also have an unsteady state capacity, so that it's able to drain the water quickly after each precipitation. The steady state capacity of the drainage layer can be estimated by the equation here. In this equation, Q is the discharge capacity of the drainage layer. Q equal to K times H times S plus H over 2L. Here, K is the permeability of the drainage layer, S is the slope, capital H is the thickness, and L is the length of the drainage layer. The unsteady state capacity of drainage layer is defined as the degree of the drainage. Usually it's measured as the ratio between the volume of the water drained since the rain stops and the total storage capacity of the drainage layer. We can apply the equation here to estimate the unsteady state capacity. Here we use T50 to measure the capacity. It's defined as a time for 50% drainage. In the equation, NE is the effective porosity. Also, the degree of drainage can be determined based on the time factor and the slope factor. The two equations at the bottom shows the estimation of TF and SF based on the permeability, thickness, length, and the porosity of the drainage layer. Here shows the degree of the drainage, which is a y-axis with respect to the time factor, that is the horizontal axis, and the slope factor. Each line represents one value of the slope factor. Basically, with a larger time factor, the degree of drainage will be smaller. In addition, by increasing the slope factor, the degree of drainage will also be smaller. The figure here shows the relationship between the time and the slope factors for 95% drainage. Basically, with a higher slope factor, the time factor for 95% drainage will be smaller. This is also intuitively correct. With a higher slope, the water can move faster to the longitudinal drain. The table here categorizes the quality of the drainage system based on the time for 50% drainage. Basically, if the time is less than 2 hours to drain 50% of the water, then the drainage system is excellent. If it's less than 1 day, then that is good. If it's more than 1 month, then we say that it's very poor. In this example, we will see how to estimate the capacity under the steady state and unsteady state. Here we assume that a drainage layer with this slope s equal to 0.02, h equal to 0.5 feet, L is 22 feet, and the permeability K is 6,000 feet per day. And the porosity Ne is 20%. It wants to find out the steady state capacity and the time for 50% and 95% drainage. So first, for the steady state capacity, Q equal to K times H times S plus H over 2L. We have the value of all the variables on the right side. K is 6,000, H is 0.5 times S is 0.02 plus 0.5 over 2 times 22. So the result is 94.1 feet cube per day per feet. So that's the way for us to find out the steady state capacity. And then we need to determine the time for 50% drainage. For the time for 50% drainage, T50, that equals to Ne times L squared over 2K times H plus SL. So Ne is 20%, that is 0.2 times 22 squared over 2 times the permeability 6,000 times H is 0.5 plus 0.02 times 22, and the answer is 0.0086 day. That is 0.21 hour. So we find out T50, and then we need to find out T95, which is the time for 95% drainage. With that, we need to call the figure about the relationship between the time and the slope factor. So we have to determine the value of the slope factor, SF. That is L times S over H. L is 22 times S is 0.02 over H is 0.5. That is 0.88. And then from the figure, we can find the time factor is 1.8. We also know that TF is T95 times KH over NEL squared. So we can derive that T95 equal to 1.8 times Ne times L squared over K times H. If you put all the values in this equation, we can get the result about T95 as 0.058 day, and that is a 1.39 hours. So that's the way for us to find out the steady state capacity, the unsteady state capacity, which is measured as the time of 50% drainage and 95% drainage. The last thing we have to consider in the drainage design is collector pipes. Usually we will apply longitudinal collectors with some transverse collectors at critical points, and the perforated, slotted, and open joint pipes can be applied for the drainage system to remove the waters. In the selection of the pipes, we need to consider the types of the pipes, location and depth of the transverse and longitudinal collectors and outlets, the slope and size of the pipes, provision of adequate filter protection for the pipes. The slope of the pipes is usually determined by the grade of the longitudinal roadway and the cross slope. In practical construction, there are some additional conditions. Usually for smooth bore pipes, the grade should be higher than 1%. For the corrugated pipe, the slope should be larger than 2%. In addition, we have some conditions for the location and depth for the collector pipes. If there isn't any significant first penetration and no groundwater, then the longitudinal collector pipes can be placed in a shallow trench, which can be shown in the figure on the right. If there's a significant first penetration, or if we want to lower the groundwater table, then we have to apply the deeper trenches, where we will put the collector pipe lower than the subbase. In that case, the backfill to the trenches should have enough permeability, and the required permeability should be equal to discharge per unit length of the trench over the width of the trench. The discharge capacity of the pipes can be estimated by the equation here. In this equation, Q is the discharge capacity in feet cube per day, N is the roughness coefficient. The table on the right shows the typical N values for different types of the pipes. Capital A is the areas of the pipes in feet square. R is the hydraulic radius of the pipes in feet. Capital S is the slope of the pipe in feet over feet. The equation here can be applied for us to estimate the required diameter of the pipes. Here, D is the diameter of the pipe. Capital Q is the discharging capacity, and Q equal to QL times L0. L0 is the distance between two outlet points. At last, let's check one example to see how we can estimate the diameter of the pipes required for the drainage system. In this example, we assume that a corrugated metal pipe is applied. The roughness coefficient is 0.024 and is placed at a 2% slope. The outlets are placed at every 500 feet, and the lateral flow is 39.2 feet cube per day per feet. So first of all, we can summarize all the information provided to us. We have the roughness coefficient N is 0.024. The slope is 2%, 0.02. The lateral flow rate is 39.2 feet cube per day per feet. And finally, we have the L0 as 500 feet. With that, we want to find out the diameter D. Then we can call the formula for D as N times QL times L0 over 53 times S to the power of 0.5 to the power of 0.375. So we have 0.024 times 39.2 times 500 over 53 times 0.02 to the power 0.5 to the power 375, which will give us the result as 4.72 inches. That is equivalent to 120 millimeters. So if we are considering some standard pipes, we should use a pipes with a diameters at least higher than 4.75. With that, we can choose someone like the diameters of 5 inches. So that's all about the drainage design. We have finished all the contents in this topic. Thank you very much for your attention. In the next lecture, we will start a new topic in the asphalt technology.